Hello! We're gonna move the mic a little bit. There we go. I think that's better. Or my audio is just turned down. There we go. Welcome back to Chem 121. I don't know where we are. It's Tuesday morning, and I'm already sick of everything. Not you guys, just like everything in general. I'm gesturing to the world right now. This is week 5, which unfortunately means that it's exam week. So on Friday, I don't have really enough space to write it down there. With only having 2 lines for my announcements. But on Friday, there is an exam. It's exam number 1, and it covers chapters 1 through 5, and we're going to do chapter 5 this week. We'll talk a little bit more about the chapter 5 quiz in just a second. We're going to finish chapter 4 today. There's only like 1 or 2 more slides to do. But quiz number 4 is due tonight and will close tomorrow. So I realize that like we have a section of chapter 4 left, and that is on the quiz, so you're gonna have to do your quiz tonight or tomorrow. But I do want to be able to get the quiz information out there, so that you have some time to study on Thursday. Oh, excuse me. Lab worksheet number 2. That's just totally different on its own. That's due tomorrow. Make sure you get those in before the deadlines. When they close 24 hours after the time's listed. On the exam, do you have 2 attempts? Yes. So you get 2 attempts on the exam, like any other online thing that you do in this course. The important thing is, though, that because the exams take longer, you need to budget enough time. If you start the exam at 10 p.m., when it closes, it kicks you out of whatever your attempt you're on, is my understanding. So if you only give yourself enough time for 1 attempt, you're only going to get 1 attempt. So don't do that. Try and take your exam earlier in the evening, like 6 or 5 or something. If you're a night owl, or if you're a morning person, just do it during the day, whenever you want to. Odds are low that there will be like an awful critical error, because that usually doesn't happen on Canvas. As far as like on your end, I cannot say. So like if you have cats that just love to eat power cords or something like that, or small children that unplug things while you're working on them, just be mindful of that. Keep all kids and or pets away from the testing area is my advice to you. Alright, so we left off last week on... Was it this slide? Because these have polyatomic ions in here. No, this is wrong. Sorry, hold on. Where were we? We were back here. That's what I wanted. We left off on this slide, which asks us to name compounds. So I'm going to go over all of the answers here for all the names. And then we'll... because we left on this slide last week, I believe. So I need a pen. There we go. So remember that the rule for naming ionic compounds is to name the metal and then name the non-metal with "ide" on it. So here's my metal. My metal here is lithium. And then O is oxygen. We're going to call it oxide. So that'd be the name of this. And we're literally just name the metal, name the non-metal with "ide." Don't add in any extra like number prefixes or anything like that. So no di, tri, tetra, etc. That's the next chapter. So don't do that on this one. Here we got beryllium chloride. And then we've got aluminum oxide. If you're British, aluminium is accepted on Canvas. I've typed in both. I'm Canadian, so I put in all of the British spelling. So like I add U's to like sulfur, and well, if you do SULPHU or whatever, I type all those in there because the sulfur is the one I don't do for whatever reason. I spell it SULFUR. But I stick U's everywhere, like color has a U in it. So I try and type in those possible pitfalls when I can, because I know that those are accepted spelling conventions. All right, there's potassium iodide. Now I got to go to the other direction here. So when we're going the other direction, we got to write down what ion forms from each of those words. So strontium is strontium. Strontium, very good. Strontium is Sr with a 2+ charge. Why does it have a +2 charge? Well, it's in column 2. It has 2 valence electrons. We ditch those 2 to get an octet. We definitely need to know that by now. Bromine has 7 valence electrons. We'll give it 1 more to give it this minus charge to give it an octet. That's where bromide comes in. And then I just have to balance the charges. I have +2 and -1. If I add another one, the charges will balance. I'll have a -2 and then +2. And then similarly, I'll just put in the answers here for these. Because presumably you've done all of them. All right, so there's our first page there. Sorry, I had to cough. Had to hit the mute button there. All right. We have the next page here, and these involve transition metals. And so these are not elements that are in groups 1 or 2, nor are they aluminum. And so when we name them, such as this one, we have to include the charge on the metal name. Now, note that there's no space here, but there is a space between the two words. So this is +4, so I would call this titanium 4 oxide. And chromium 2 sulfide. All right. And then down here, the last thing that we can do. So if I have gold 1, that would be Au with a plus charge. Chloride is just this. That could look better. That would be gold 1 chloride. What about sodium nitride? That would just be that. What about barium oxide? That would be that. And then platinum 4 would be PT4 plus. Fluoride with F minus, PTF4. There you go. So the middle two are just from the previous slide. I just didn't have enough examples, I guess. I don't know. Okay, so that's our review on how to name ionic compounds. The next thing that we're going to do is we're going to talk about polyatomic ionic compounds. Now, the polyatomic ions are at the start of chapter 4. So this is referring to all of these in this table on slide 2 that you were tasked with, quote-unquote, memorizing, but this is not an in-person class. So just have this reference handy. But whenever you see one of these ionic compounds, so like let's say that the formula you were looking at was this, then what you would do is you would say, okay, well, I name the metal, so that's sodium, and then I name the non-metal, and what you do is you just take this name. So this would be sodium nitrate, and that's it. You just use the name right off this chart. You don't make any adjustments to it. So now I gotta go find where we were. There we were. So in other words, if I go to this formula that I had here, so this, if you ever see a polyatomic ion, you just drop it in the whichever box that you have here. So you don't have to do anything with I, you don't have to do anything with the metal. You just drop the name right in there. So here's another example What would this be called? Well, the first thing that's positively charged is ammonium, so we would just put ammonium right here. It's not a metal, but we just drop it in the box anyway because it's the cation. And then this is bromide. So this would be ammonium bromide. So whenever you see polyatomic ions, just drop the name right into the box. So let's do some examples here. So based on this and what you know about your polyatomic ions, and you can go back to the second slide if you need to, what is the name of this substance? I'll give you a second to type it in the chat. All right, so what is K? Well, we're going to name the metal. And then what is CO3? According to the polyatomic ion sheet, that is carbonate. In fact, the term carbonated, as in carbonated beverages, comes from carbonate because the acid form of carbonate is what contributes to the tart taste of a carbonated beverage. Now, again, remember, Canvas doesn't like capital letters for these because it's expecting exactly this. This is supposed to be lowercase, and the reason it's capitalized is because PowerPoint is treating it as the start of a sentence, and I didn't go back and fix it. So just be mindful of that. That the answer is supposed to be all lowercase letters. However, proper grammar rules do apply. So that's why I typed it like that. All right, how about this one? What is this called? Type your answer in the chat. All right, so this is barium. And then OH, according to the polyatomic list, is hydroxide. There you go. Very good. All right, I'm going to give you a bunch of these. Go ahead and name them in the chat. So we'll go 1, 2, 3, 4, 5, 6, 7. And yeah, you'll need to either have memorized the table of polyatomic ions, which don't do that. I mean, you'll need to eventually, but don't do that now. Just have it handy. Or have that bookmarked. So just have it like on your screen when you're taking the exam. You can tab over to it. That's fine. I'll give you 5 minutes. We'll go over the answers in just a little bit. See you soon. One more minute, we'll go over the answers. All right, so let's look at this first compound here. I've got ammonium and sulfate. And you can just recognize those from the list of polyatomic ions. Now, there is a space here. It's just kind of hard to see. So there is a space. And we got potassium, which everybody knows. And then we've got hydrogen carbonate. Now I'm making my spaces really big, I guess. There we go. And then we did sodium nitrate on the other slide here. And then we got lithium cyanide. Fun fact, if you eat almonds, the almondy taste is cyanide. Cyanide is a very, very, very low concentration that is present in almonds, and that's what gives them their distinct almond flavor. Which is kind of strange. But there you go. All right. Now, this is a little more tricky. So here we got sodium. That's Na+. Then we got hydrogen carbonate. And if you look up the formula for that, that looks like this. So the non-metal one is either one letter of two. I'm not sure what you mean. So I am specifically looking for the polyatomic ions. So basically, I'm looking at this list here. And I'm trying to find any of these that are in my formula. So here was cyanide. So I saw that was there. So if you recognize these patterns, this is the name of them. And so that's your task, is when you get these questions. Where am I? We're here. Okay. To just look for those. So I can pull out the highlighter here, which... So here's a polyatomic ion. Here's a polyatomic ion. Here's one. And so on and so forth. So when you're asked for the formulas, I haven't finished this formula, sorry. But when you are writing the formula, you treat this just like you would for any other ionic compound. So here are the parts of my formula. I'll balance out the charges, and then there should not be any charges in them. So there's my formula. Ammonium chloride. Ammonium is this. Chloride is that. We'll put them together. And then finally, we've got potassium, which is this. We've got phosphate, which is this. So we'll put them together, but I need more potassiums, right? I only have one to counter this 3-, so I need 3 total. So there would be my formula. So treat it like all of the other ionic compounds that we've done so far. Yeah, you always have to balance, because remember, if you have leftover charges, it'll attract other things to it, and the formula changes, right? All right, I got 4 more. So I'm going to give you 2 minutes to name these, because more practice. Hooray. One more minute. We'll go over the answers. All right. So, same sort of idea here. So these first two shouldn't be anything different. So calcium is just this. We got sulfate, which is this. I can put those two together to cancel out the charges. And then rubidium here and hydroxide also go together to just sort of cancel out the charges. Because I got 1 and 1 of each. Up here I had 2 and 2 of each. Over here, however, I don't have as much luck. So these charges don't directly cancel each other out. So I need to add multiple of something, right? So nickel 2 is +2, but cyanide's only -1. So I need an extra one of these, right? And so the formula actually ends up being this. Now, when you have multiple of a polyatomic ion, which we're going to see in the next section here, you have to use parentheses, because if I didn't have the parentheses here and I did this, now I have an error, right? Now it looks like I have 1 carbon and 2 nitrogens, but in reality I have 2 cyanides. So the parentheses are just there to collect your polyatomic ions. Down here, same idea. So molybdenum 6 has a 6+ charge. That's really positive, right? Phosphate is this. In order to counter this 6+, I need 2 phosphates, right? So that means that my formula would become MO parentheses PO4 2, because I have 2 phosphate. There you go. All right. Now I have one last little set of these, and it deals with parentheses. So this slide is just talking about, hey, use parentheses. This is what you want. You do not want this one right here, because this looks like, oh, hey, I'm only putting the 2 for the hydrogen and not the oxygen. And so we just did these examples. So I'm going to just give you the homework practice there. Look how many homework practice problems there are for naming. Yeah, the textbook has like 50 problems, which is absurd, but naming is complicated. Go ahead and name these 4 compounds, or not naming them, but write the formula based on these ions. And then if you want, you can name them. All right, one more minute. We'll go over the answers to these. All right, so for these formulas, I've already given you the ions. So we would say, okay, I need 2 positives to balance out this 2 minus. So I would write NH4 parentheses 2. Oh. And then if I wanted to name this, I would name it ammonium oxide. All right, down here I have positive 2 and negative 3. And I'm sort of limited on space, but if I had 3 of these over here and 2 of these, I would have a total of 6 positives and 6 negatives, and so the charge would balance out. Now, I don't need the parentheses for the barium part, but I do for the phosphate. And there's that. Then we got aluminum and nitrate. So I need 3 nitrates to pair with my aluminum. There you go. And then same idea down here. If I have a 3 and a 2, I need 2 of the one that has the 3 plus charge, and 3 of the thing that has the 2 minus charge. And that would look like this. Oh, I forgot to name these. I'm sorry. So this is aluminum, and this is nitrate. This is iron 3. There we go. Sulfate. Why is there a 3 by the barium? Because I need to have 3 of them in order for the charges to balance out. So, you know what I can do? I could just go over here. So, this is just like the ionic compounds that we were making earlier. So, if I write out my... Let's see here. There we go. All right. Do my charges cancel out if I have it like this? Well, no, they don't. So I need more of these. I still don't cancel out. So I need more of these. Well, they still don't cancel out. Oh, there we go. They cancel out, right? I have 6 of them on both sides. So this is what you're doing for ionic compounds. So what we did last week when we were naming these. So, and then the week before when we were constructing these. So now my formula is just, okay, how many did I use? Well, I had 3 barium and then 2 phosphate. So there's the formula. And so we're doing that for all of these ionic compounds. The rules that we applied previously have not changed. We're just looking at different circumstances to do these. All right. That's chapter 4, I believe. So let me know if you have any other questions about it. Happy to answer them. But we do need to get on chapter 5, so let's do that really quickly. Oh, I just realized you can't hear the little hooray music. Here, let me do that again. There we go. Yay, everybody likes that. Screen will go black for just a second while I get the chapter 5 slides up. There we go. Do we need both the name and the compound, or just would one be enough? It depends on what I'm asking you for. So, in that case, I was just asking you for the formula. All right. So what we're going to do today is we're going to learn how to draw covalent compounds. Covalent compounds are different from ionic compounds. In ionic compounds, our goal was to just shuffle electrons around to get octets. And that was generally done by... yawning, excuse me. That was generally done by us having a metal that gave away an electron and a non-metal which accepted the electron. And we just shuffle the electrons from the metals to the non-metals, and then everything would work out. With covalent compounds, it's a little more complicated. Now, how do we know that covalent compounds do something totally different for bonding? The evidence is that the compounds that we observe have totally different chemical and physical properties. Sorry, I'm reaching down to move something so I can move the heater closer. Oh, this is not what I want. It's so cold in my apartment today. It's May. I'm so sick of having to use a heater. There we go. All right. So the evidence for covalent compounds being very different lies in the fact that there are properties that are just completely foreign to ionic compounds. For example, all ionic compounds that we study are solids at room temperature. Excuse me. And their melting points are extremely high. So melting table salt or any other ionic compound is tremendously difficult. But melting things that are covalent, such as water, is very trivial. Water melts at room temperature. In fact, oxygen and nitrogen, the gases that are in the air, have already, not only have they melted to a liquid, they have also evaporated from liquid to the gas phase at temperatures well below that of room temperature. In fact, if the temperature gets down to like minus 150 Celsius, that would be when oxygen and nitrogen would become liquids. Fortunately, we don't have to worry about that. We're not going to have a minus 150 Celsius day. This is not Frostpunk, where it rains liquid oxygen and nitrogen. That'd be terrifying. Now, there are other substances out there that have other strange properties compared to ionic compounds. So ionic compounds like salt is very crystalline, but something like wax is not a crystalline solid at all. You can kind of mold it with your hands. If you've ever had a candle, and the candle is even like remotely warm, you can change the shape of the candle by just pressing your hands into it. If you drop a candlestick, it'll actually snap in half, whereas ionic compounds won't do that. It's very hard to cut ionic compounds. You need a lot of force to do that, but candles, you could just, oops. So, there are tons of different compounds out there that don't resemble ionic compounds at all, and so what our conclusion is that the bonding in these types of compounds must be unique. It cannot be the same as an ionic compound. So in the ionic compound drawing that we did for Chapter 4, where I showed you the lattice, let me go over here really quickly. We said that an ionic lattice was how we observed ionic compounds. And so that would look something like this, where the charges just alternate. And you get the point. And this also continues on in all directions. I'm trying to draw like coordinate axes here. So I've drawn like one sheet of ions, and so this would be our lattice. Now, the reason that the lattice is so strong in terms of melting point, boiling point, etc., is because every ion exhibits charge in all directions, right? So this ion right here is attracted to this neighbor, and this neighbor, and this neighbor, and this neighbor, and whatever neighbor would be in front and then behind it. So it is locked in place. It is there, and it wants to be around all of its neighbors, because opposite charges attract, and those charges propagate in 3 dimensions. Now with covalent compounds, so something like this, we have molecules, which I'm going to draw as circles. And so there are no bonds between these. So this molecule, if it wants to go this way, it can. This one can go this way. And our molecules just sort of bounce around. But there's nothing holding them to each other. At least as far as we're aware of yet. We'll get to that at the end of Chapter 7 or so. And so because there's nothing holding these together, the boiling point will be low versus the boiling point over here, which will be high. Now, that does mean that if we look at the bonding that occurs in molecules, what we're going to see is that all the molecules bond internally. All the atoms within the molecule are bonded together, but we don't make any bonds outside. So let's go look at how we do that. All right. Now, the gist of bonding is the same in ionic compounds as it is in covalent compounds. Atoms want octets. This is just a fundamental feature of matter. But there is an issue with covalent compounds. If they want an octet, they have to do it a different way. And the reason for that is the following. Let's suppose that I had 2 fluorine atoms, which we're going to see in a second here. So here's a fluorine and here's a fluorine. And so we're going to pretend that this is ionic. So I'm going to move this electron over here. Does everything have an octet? Well, this one does, right? But now this one is 2 away from an octet because it gave up 1. Sorry, I can't stop yawning. I just haven't gotten enough sleep this week. So when I try and do this scheme that I've drawn on the board here, it doesn't work, right? I cannot get to an octet for both fluorines by moving electrons and transferring them from one atom to the other. Whoever I take the electrons from will always be deficient. So the ionic model that we tried for ionic compounds, and it worked great, but if you only have nonmetals, this isn't going to work. In fact, there's no way to do this. So what we have to do is we have to do something different. And that different thing that we do is that instead of transferring electrons, we share them. Now, what does it mean to share electrons? We're going to show a picture of this in a second that'll make it very clear. This on the board that I've drawn in red down here, this is transferring electrons. This is from chapter 4. Let's share electrons. But first, we're going to define any compound that shares electrons is called a covalent compound. And that the shared electrons form covalent bonds. All right, let's share some electrons. So here's my fluorines. Sorry, this slide is just asking you to draw Lewis structures for fluorine. And what we're going to do is we're going to cause these electrons to be shared. And the way that that's going to look is like this. Now, what are the electrons that are shared? It's these 2. I'm going to separate them out again. And you'll notice that I have unpaired electrons on my fluorine, and I'm going to invoke sharing. All right, everybody, let's share. Okay. All right, we have shared. When we share electrons, we share the unpaired electrons that are available. Where did my cursor go? There it is. Okay. We share the unpaired electrons. And so any electrons that are by themselves are candidates for sharing. You'll notice that over here, these ones that were already paired, they just stay the same. Nothing happens before and after we form our bond. So if there are electrons that are already paired, you just leave them there. But the paired ones, those get shared. Now, what is the consequence of this? Well, if I look at these and count the number of electrons around each atom, I could circle them like this. And what do you notice about the electrons that are shared? Oh, look, they're double counted. That's interesting. But atoms are stupid. They don't realize that the electrons in the middle don't exclusively belong to them. They're just concerned that, hey, I have 8 valence electrons in proximity to me. I am happy with this result. So that's going to be our goal. We're going to accomplish the octet rule by sharing electrons. Now, drawing out molecules is more clear if we use this notation, where the electrons that were shared here, let me get the highlighter out here. Oh, come on. There we go. So there's my electrons. We're going to just write this as a little line. And so the line represents the bond of shared electrons that we've made. So are they stable like a noble gas? Yes, they are more stable than they were before. Now, things that have formed octets may still react, but they are less reactive than before the octet was formed. So, for example, if I have F, just the fluorine atom, so 7 valence electrons, fluorine atoms are viciously reactive. Fluorine gas is still quite reactive, but it is less reactive than F by itself. All right, so our shared electrons form the covalent bond. Now, the electrons along the outsides here do have a name. They're called the non-bonding pairs. Non-bonding pairs hang out. The reason that we care about them is we're going to get to this not tomorrow, but Thursday. We're going to talk about space around the atom. How big are molecules? Where do electrons live? Those electrons in the non-bonding pairs take up space. So we're going to be concerned with that space that they take up. Now, when we do these bonds in our structures, it's very important to remember you're only using the unpaireds. And every time you pair up 2 individual unpaired electrons, you will create a bond. Bonds are drawn as lines, but it's easy to forget that your lines each represent 2 electrons. So if I have something like this, then there are 2 electrons in that bond. And then again, remember, our goal is to hit the octet here. Everything wants an octet. So you should have 8 electrons around an atom. Now that might look like this, or it might look like this, or it might look like some combination of those. But as long as there are 8 electrons around your atom, you've satisfied the octet rule. And that can be in the form of dots, where each dot is an electron, or lines, where each line is 2 electrons. Now, there is one exception to this, and that is helium and hydrogen. I say one exception because hydrogen's really the only one. Hydrogen just wants to look like helium. Hydrogen only needs 2 electrons. So for hydrogen, you will always just see something that looks like that, and that's it. Hydrogen can never form more than 1 bond. It's too tiny. There are just not enough space in the smallest layer of electrons for any more than 2 electrons. All right. So we are due for a break. So I'm going to put the timer on the screen here. Where is my timer? Oh, it's minimized. That's why it doesn't show up for some reason when I do that. All right, so I'm going to start this. We're going to get some more Mega Man music going. I'll answer any questions that are in the chat still, and we'll see you in about 10 minutes. All right, we're back. So now that you have seen how we can make bonds, what we're going to do is we're going to take different atoms and try and pair their unpaired electrons together. So for instance, with Cl2 here, if I draw the Lewis symbol for chlorine, and I do that again for another chlorine atom, can I find a place where I can share 2 electrons? And it turns out that that place would be, something obvious thing, right? There's only one pair that I can create, and that'd be this one, right? So my molecule would look like this, a Cl and another Cl, and the unpaired electrons are bonded together. So what I want you to do is I want you to do that for each of these. Draw out the Lewis symbol of each of the atoms individually, and then try and connect up the unpaireds to form bonds, and you're going to create simple Lewis structures. We're going to do a much better way of doing this later, but this is just a concept check. So I'm going to give you 3 minutes to play around with this, and then we'll go over the answers. Oh, hold on. Sorry, I was dropping frames. I'll give you 3 minutes to do this, and then we'll go over the answers in a little bit just after that. One more minute, we'll go over the answers. All right, so let's draw some of these out. We'll have to go over here to do this. So we already did Cl2. Get rid of this. So what we're going to do is we're going to draw BRF. Let me do this so that I can draw everywhere. So if I want to draw the Lewis structure for bromine, bromine has 7 valence electrons because it's in group 7. So does fluorine. So there's those. And because I'm in Photoshop, I could just do this and say, "Woo, we're going to pair them." There we go. And then we would replace our pair that we made with a bond. There you go. All right. How about this next one? So CF4, if I draw carbon, carbon has 4 valence electrons. It looks like this. And then if I draw fluorine here, that looks like this. Now I'm too lazy to draw this 4 times, so I'm going to go copy, paste, paste, paste. I don't really have space for it, so we'll just stick that over there. Now, what I can do is I can do this. I can put this guy here. So that's going to be shared. I can put this one. Oops, I grabbed the wrong one. We're going to rotate him. We're going to do that. All right, so he's now in there. And we're going to take this one, and we're going to rotate him. Now, I'm going to fix the orientation of the letters in a second here, but you can see what I'm trying to do. Oops, oh, that's not going to work. Hold on. So if you think of these as like little puzzle pieces, so there we go. So now we got this. We're going to rotate him. There you go. And then I need to tidy up my structure, right? So obviously I need to have all my fluorines pointed the same direction. And then the electrons in the middle would be shared. So we'll draw lines. The remaining non-bonding electrons on the outside we'll just draw in. Now, how did I know that I had 4 valence electrons on carbon? It's because it's in group 14. So it's based on where it is on the periodic table. Remember that whatever group you're in, you use the ones digit. All right. So you can think of all of these atoms as just being like little puzzle pieces that we can drag around. And so that's why we have this crazy like fluorine thing where the fluorines are all rotated around there. Now for water, same sort of principle here. So here's oxygen. Oxygen's in group 16, so that means 6 valence electrons. I've got 2 hydrogens. And I can just take this one and move it right here. Well, I'm going to have to rotate this. So there's one. And then there's the other. And then we'll tidy up. And there's water. And hey, you've probably seen that structure for water before. That's how you get it. Where you see the O in the middle and the H is on the sides, and it's bent at an angle. And it's bent at an angle because of the electrons there, right? I mean, sort of. We'll get to that in more detail later. All right. That's the basics of how we form bonds, is you just pair the unpaired electrons together to create bonds. Now, we've been using these as puzzle pieces where I could just move independent pieces around however I need to and then pair up their unpaired electrons to make a bond. But what happens when you get really complicated molecules? Then having all of these individual atoms that we're going to move around is going to be super tedious. And in fact, it's going to be counterproductive. So later on, what we're going to do is we're going to adapt a better model for drawing Lewis structures. But for now, this is good. This is just a model that we're going to use to help us learn. So now, it becomes possible to make multiple bonds between any two atoms if you have multiple unpaired electrons. So let's see that in action. Here's oxygen, O2. Now, in theory, I could say, okay, I'll just bond this to some atom and this to some atom, and I'll just make two bonds to other atoms. But what if I chose the same atom for both of those? That'd be something like this. So I could take my oxygen molecule to connect each of these unpaireds with another unpaired on oxygen. And the result would look like this. Now, every time I make a pair, I just treat it as a line, right? Because the line represents two electrons. So I'm going to go 1, 2 lines. So this would be a double bond. A double bond is 4 electrons. It's 2 pairs of 2. All right. Now that you've seen oxygen in action, I want you to try and do this for nitrogen. First, draw the Lewis structure for nitrogen. Nitrogen, the atom. And then try and bond 2 of them together. And tell me what you get. Tell me how many bonds you get. I'll give you 2 minutes to try that. We'll go over the answers in just a second. All right, let's draw what we get. So if I have nitrogen here, and I draw its valence electrons, I see that I have 5 valence electrons because it's in group 15. If I draw a second one of these, I could then pair these electrons and these electrons and these electrons. And when I tidy up, that'll look like this. And I get a triple bond. Since each line is 2 electrons, a triple bond must be 6 electrons. All right. What's the maximum number of bonds you can make to something? Well, if I were to do carbons together, you'd notice that, oh, okay, well, maybe I could just connect all the electrons together, right? We'll do this other question in a second here. So I could do this with carbon, so I could easily make a triple bond for carbon. But this fourth bond would require me to make a bond going around, right? They're just pointed in the wrong direction. And it turns out there's no way for me to bond everything together, because I can never get the correct orientation in space. This last site will always point at something else. So I can't do this. And the maximum number of bonds between 2 atoms is 3. Why is it 6 electrons? Because remember, each line is 2 electrons, so 2 electrons per line. And then 2 times 3 would be 6. All right. Now what I want you to do is I want you to draw C2H2 and C2H4. And I want you to tell me which molecule has a double bond and which one has a triple bond. And tell me what you observe about those molecules as you've drawn them. I'll give you 2 minutes for that. We'll go over the answers in just a bit. All right, 1 more minute. We'll go over the answers. All right, so let's go over here. All right, let's draw C2H2 and C2H4. So now, in order to make this work, I need to have some number of bonds between my carbons, and then the H's have to fill in the remaining spots. Now, I can't just leave unpaired electrons. So if I did something like this, and then connected these H's here, this doesn't work, right? So this is no good. I need to always have my unpaireds bonded to something, some other atom. So let's undo all this. So if I do something like this, and then this other carbon gets a hydrogen, now I can just bond these guys together. And then when I tidy that up, that would look like this. Now, why am I drawing all these lines all over like a football diagram? So this is just our plan here. And then this is our Lewis structure. So in the planning phase, you can draw whatever the heck you want to, right? But we do need to straighten up all of our bonds because bonds are in straight lines. So there was C2H2. Let's look at C2H4. We're going to follow the same principle here. You're probably noticing that this method of, oh, I'm just going to connect the dots is not really working for us anymore, right? Because the correct solution for this is actually to say, okay, I'm going to connect 2 hydrogens on this side. I'm going to connect 2 hydrogens on this side. And then I'm going to connect the remainder. And so that ends up looking like this. But this is going to get obnoxious really quickly. As I add more pieces, it gets more and more complex. So there's got to be an easier way to do this. Now, it doesn't have to be symmetrical, but most of the time it will be. Nature likes symmetry because in all of our bonds here, all the bonds contain electrons, and electrons repel each other, right? So you don't want to have all the electrons clustered in one area. You want them as spread out as far apart as possible, and the symmetric arrangement does that. So there are physics reasons for why things will look symmetrical, and it's not always going to be the case, but for our examples, 99% of the time it will be. If it can be symmetrical, it will. All right, so those are our simple Lewis structures. There's the homework practice for this section. And you'll notice that this model, not so great for bigger molecules like C2H4. So we're going to devise a new model, and so that's what we're going to do in this section. This will be the last thing we do today, probably. We can do geometry tomorrow, or Thursday, or whatever. All right. How do you make a larger molecule? We're going to follow what I call the 5-step plan. And the 5-step plan is a guideline for how to make the Lewis structure for virtually any molecule I throw at you in this class. Now, very important for the 5-step plan, you must do these steps in this order. If you are unable to do one of the steps, you skip it and you don't come back. The first 2 steps are required. After step 2, steps 3, 4, and 5 may or may not come into play. Most of the time they will. But if you find yourself unable to do a step, like, oh, I can't do this step because I don't have enough electrons available in my model, you skip it and you don't return. All right, so let's do the 5-step plan. For any molecule that you are given, you are going to have some number of valence electrons. You might have noticed that this is called covalent bonding, right? That's because they use the valence electrons communally. That's where the name comes from. And since we're drawing valence electrons around our atoms all the time, we could just count them. That should be an E. Here's my oxygen. How many valence electrons does oxygen give you? So if I had to draw the Lewis structure for CO, my total would be, oh, there we go, 10. So any molecule that you're given, you're going to be able to count the number of valence electrons by just summing all of the total valences together. Carbon is 4, oxygen 6, hydrogen is 1, nitrogen's 5, so on and so forth. All right. Once you have counted your electrons together, you're going to have a pool of electrons. That pool is going to be the number of electrons you have to draw anything. And then we're going to construct a skeleton of a molecule using those electrons. So the first thing that we're going to do is we're going to take our framework by just writing the atom some random place in space. So for instance, if I was given HCN as my target molecule, I would just do something like this. If I had CO3 for carbonate, I would do something like this. And what our job here is to do is to write some atom as the central atom, and then everything else goes around it. The first atom is the central atom, unless it's H. H can never be the central atom. Then it's the second atom. So the central atom is first, but not H, except H. And so what we would do is just somewhere in the paper, draw your central atom, and then put all the other atoms around it roughly equally. And then the next step that you're going to follow is that you're going to connect everything together. Now, do you need one bond to do that? Do you need two? Who knows? We're just going to figure that out later. For now, we're going to just put bonds between all of our atoms. Each bond that I draw, again, is 2 electrons. And because I have a count for my valence electrons that I did for step 1, we're going to start deducting electrons from that. And then steps 3 through 5 are just use the rest of the electrons that you counted in step 1. And so I'm going to put those steps on the board here. For your structure, you're going to just fill in electrons around outer atoms to complete their octets. Anything left over goes on the central atom. And then step 5 is a catch-all. Oh, I ran out of electrons before I could get everyone an octet. Here's my solution. Make multiple bonds. We're going to see examples of this as we do practice problems here and there. The first problem I'm going to do is carbon dioxide, and we're going to use these 5 rules to draw it. So let's do this. Oh, pen is touching the tablet. That's no good. Moves my cursor to the wrong monitor. There we go. Okay. All right, so what we're going to do is we're going to draw the Lewis structure for CO2. And I'm going to write out the rules here on the left here. So remember, for our 5-step plan, rule number 1, count your valence electrons. All right. What's our target molecule? It's CO2. How many valence electrons does each atom give you? So carbon, group 14, 4 valence electrons, right? Each oxygen is going to give us some number of valence electrons. I need to multiply however much one oxygen gives me by 2 because I have 2 oxygens. So that would be this. Oxygen's in group 16. It has 6 valence electrons. How many total valence electrons do I have to work with? Well, 6 times 2 is 12 plus 4 is 16 electrons. In my structure. So what that means is that when I draw the Lewis structure of CO2, I can have no more or no fewer than 16 electrons. I must use exactly 16. If I draw the structure and I have 18 electrons, I'm not drawing CO2. I'm drawing something different. The most common mistake in drawing Lewis structures is that you miscount the electrons. Students will ask me all the time, like, hey, I didn't get what you got. What's wrong? And then I'll count their electrons and go, oh, you have 20 electrons, but you're only supposed to have 18. And then it's immediately like, oh, duh. It's the counting. It's always going to be the counting. So just be meticulous with your counting and you'll be in better shape. All right. Step 2, we're going to draw the framework. What's the central atom? Well, the central atom is the one listed first, as long as it's not hydrogen. So there's my atom in the center. I'm going to just draw stuff around the sides. And then I am going to connect each of my atoms to the central atom. Remember that bonds are electrons. They cost electrons from our total. So I had to withdraw 4 electrons because I used 4 electrons to connect the carbons to, or the carbon to the oxygens. All right, so we've done that. Now let's do step 3. Which is to give electrons to all the outer atoms to fill their octets first. So that's easy enough to do. So we'll go 1, 2, 3, 4, 5, 6. So I have 6 left. 1, 2, 3, 4, 5, 6. All right, so I've used all my electrons. There's my drawing so far. We're going to get rid of these right here. Because my next question to you is, does everything have an octet? So if I circle this oxygen, remember lines count as 2. So 1, 2, 3, 4, 5, 6, 7, 8. This has an octet. This oxygen is happy. What about this one? Lines count as 2. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is happy too. What about this one though? 1, 2, 3, 4. Uh-oh. Uh-oh. There's not enough electrons around my carbon, so the structure is not done. I do not have an octet for everything. We'll go on to step 4. Step 4 is put any remaining electrons on the central atom. But there's a problem there. I don't have any electrons. So I can't do it. So we go to step 5. Which is, we have to make multiple bonds. And the way that multiple bonds works is very straightforward. I get rid of electrons on an outer atom, and I create a bond to an inner atom. Do I still have an octet? Well, if I circle this, 1, 2, 3, 4, because bonds are 2, 5, 6, 7, 8, I do have an octet there, don't I? All right. But my carbon is getting closer to an octet. So let's do the same thing here. I'm going to go like that. I'm going to put this here. Again, the symmetry thing comes up because it's just easier to do for nature. It's lower in energy. And then finally, when I check for octets everywhere, my oxygens are fine. But what about this carbon in the middle? Well, each line counts as 2. There's 8 lines. Everything is good. So there's our structure. CO2 is a carbon double bonded to an oxygen, double bonded to some other oxygen. Those were not supposed to be in series. The carbon is what is bonded to both oxygens. Sorry, I'm drinking my water and then I'm drawing what I said in my head and I'm like, wait a second, that didn't come out right. All right, so we've all seen this in action. So now I want you to try it. So my slides walk through the steps here. And there's our structure. So I want you to try and do this, for ammonia. Now, ammonia you could do with the just connect the dots method, but I want you to do this by tallying up your valence electrons. Draw out the framework, and then put all the dots down. Remember, hydrogen can only take 2 electrons, so if you bond it, it's done. I'll give you 2 minutes to try it. All right, one more minute. We'll go over the answer. All right, so for ammonia, let's follow the 5-step plan. So first we'll count our electrons. You should have gotten 8. Then we'll draw a framework. So I'm just going to put hydrogens around this somewhere. We're just going to sort of spread them around as evenly as we can. And then step 2, we're going to connect these. So that would be 6 of our electrons, because each line is 2. Then for step 3, we have to put electrons around outer atoms, but all the hydrogens need is 2 electrons, so we don't have to touch those. We'll go to step 4, which is to put the remaining electrons on the central atom. And then everything has an octet except for hydrogen, which only needs 2 electrons anyway. So this is the correct structure. And when I hit spacebar, it'll appear right under it. And my picture is at right angles because I was drawing that in a different program. And that's just what it does. But if you didn't draw yours at right angles and you drew it like mine is like the letter Y, totally fine. It doesn't matter. All right. I'm going to give you a bunch of these now. And what I want you to do is I want you to draw the Lewis structure for all of these using our 5-step plan. Now, you're going to need more than 6 minutes to do this, so I'm going to let you try this for a bit. I'm going to do 1 or 2 of the answers, or I'll give you all the answers at the end of the period, because we only have about 6 minutes left. So try and do this for 5 minutes. I will just draw the structures on the screen for you. And then we'll go over the answers when we come back on Thursday in more detail. So try these now, and we'll see you in a bit. All right, we are out of time, but what I'm going to do is I'm going to put all the answers for these on this screen right here. So here's all the answers for the 5 problems here. Let me put all of these on the screen so you can see what those problems were. There you go. So there's the 5 Lewis structures. You could pause the video if you need this to compare your work with. And if people have questions, we can go over these next time. I just wanted to get the answers out there so that you could see them. But really, it's just follow the 5-step plan. Count all your electrons, do your framework, outer octets first, then inner octets if you have leftover electrons, then make multiple bonds to fill everyone's octet. All right. I want to thank everyone for coming out to the lecture. When we return on Thursday, we're going to talk about geometry, polarity, and naming. So we're going to have 3 last topics to go through. All of those are things that are going to show up on the exam on Friday. So I would definitely recommend that you brush up on some of those topics now by reading ahead of time, because they'll show up on the midterm. Regarding quiz number 5, what I'm going to do is I'm going to open it up tonight. It's going to be due a week from today, we'll say. But what I'm going to do is I'm going to have it display the answers after you've taken the quiz. So you still get 2 attempts, but after Thursday's lecture, you could immediately take the quiz for practice, and you'll be able to see the answers for the questions that you got. And you can use that as a study aid. So it's just because we're slightly behind that the Chapter 5 quiz will be so close to the exam date. I need to open this thing. I never have this open because I have too many things open on my computer at once. But yeah, there we go. All right. That's all I got. Make sure that you get quiz number 4 in tonight. Now that we're done with Chapter 4, you can actually do all the problems. That will close tomorrow night, and it will open on Thursday so that you can study for the exam on Friday. Lab worksheet number 2 is due Wednesday, and then the exam is on Friday. I'll see you on Thursday for the next lecture. Let me know if you have any questions. Take care.